Hi, I'm Akshay, and this is the networking preview session for OSDI and ATC 2021. There are two networking themed preview sessions this year, and both are ATC sessions. The RDMA session, and by the way, if you don't know what RDMA is, I'm going to explain, and you're listening to the right video, is the first track one session on the first day of ATC, and the session with all of the other networking papers is the second session on the second day, also in track one. The goals of this preview session are to understand the underlying technologies that the papers in the two sessions use and what problems they might want to solve, as well as provide some questions that you might want to keep in mind when thinking about the papers during these two sessions. What I'm explicitly not going to cover is technical details about the papers. I'm going to leave the authors to do that, and you should listen to them about their work instead of me. I also have no idea, by the way, why the session's names reference dogs. I guess you can ask the PC chairs for clarification on that question. So the first session is about RDMA, and it's probably a good idea for us to talk about what RDMA is and why people care about it. So RDMA is a paradigm for inter-server communication. It stands for Remote Direct Memory Access. Normally, which is on the left side on the slide here, when a server receives some data, the CPU has to do some work to figure out what data is and where in memory it should store that data. This indirection from the NIC to the CPU to then write to memory can be considered wasteful, and now we have RDMA. With RDMA, you buy a special NIC, which knows how to talk directly to memory without involving the CPU at all. This has both upsides and downsides. The CPU, which is slow compared to NIC hardware, doesn't need to spend any time processing packets. It can just tell the NIC when another server has something to send us, just put it in this designated piece of memory, and I'll come get that, read that piece of memory later. So from the CPU's perspective, data just sort of magically shows up in memory when other machines send things to us. The main downside of this is that you need this fancy NIC, and often you need a fancy network to go with it. So RDMA has some weird historical quirks for most of us who are used to Ethernet everywhere because it originated in the high-performance computing, or HPC, community. Because it originated in supercomputer clusters like this one in the picture, RDMA is a little bit different. So for one, cluster computing people don't need to care about interoperability with the rest of the internet. So they designed their own special network, which they did, and they called it InfiniBand. InfiniBand has a couple unusual qualities. So for example, the network fabric itself is lossless. So once a sender sends a message, it forgets about it, and it can be sure that the network will deliver that message. And this is obviously very different than what we're used to with IP over Ethernet. And originally, the reason to use InfiniBand is that it supported much higher bandwidth and lower latency than Ethernet, and this is why it was very attractive or developed for the HPC community. But once data centers started to get big, it didn't take long for smart people to sort of look at them, squint, and say, hey, these things could probably learn lessons from supercomputers that have already been built. So on the other hand, though, people still liked Ethernet's flexibility, so RDMA today is often deployed on a protocol called RoCE, or RDMA over Commodity Ethernet. This is basically Ethernet pretending to be InfiniBand, so a lot of the same features like losslessness are still available, they're just implemented in different ways. In data centers especially, one of the benefits of RDMA is that a lot of the time, the point is to sell CPU cycles to some customer. So if the CPU is doing less work moving packets around, then you can sell more CPU time to customers. You have more CPU time to sell. On the downside, you now have to buy this new fancy NIC, which can be complicated and needs a fancy network, and that costs money. Also, you generally have to use this special API, which is usually a library called libibverbs, instead of the familiar sockets API that you're used to in order to write your applications. Conveniently, the whole point of a company is to make investments in order to sell things. So in this case, our company can invest in RDMA-compatible NICs and rewriting their applications and recoup those costs later by selling the extra CPU cycles that they're no longer using to cloud tenants. And at least one major cloud provider, Microsoft, has done exactly this, and it seems to have worked for them. And if you're interested in learning how they made it work, I'd recommend this paper, RDMA over Commodity Ethernet at Scale, from SIGCOMM 2016. One interesting area to take note of is that RoCE is not the only way to do RDMA. There's another protocol called iWarp. The philosophy of iWarp is that the NIC should handle all the complexity of dealing with a commodity network. There's a definite advantage to this approach. So reading the Microsoft paper will tell you that configuring networks to deal with RoCE can be very complicated. But on the other hand, moving everything to the NIC can also be complicated since someone has to implement those features in your fancy NIC hardware, and complicated hardware tends to be both slower and more expensive. The ultimate answer to this question is going to depend on which set of salespeople you talk to. So Mellanox is a company that is very pro Rocky, and Chelseo is a company that is pro iWarp, but there are valid points on both sides. So now that we have some idea of what RDMA is, I'll leave you with some questions you might want to consider. So first of all, using RDMA, as we've covered, is a hassle. So there's a different API, this libivverbs API involved, and we have to use a special fancy NIC, and we might have to configure our network very carefully. And as a result, when thinking about applications and settings, one thing to evaluate is whether this hassle is worth it to us for our specific application. So in other words, what are the costs we pay for what performance benefits that we get? If we can lower the cost, for example, by making the RDMA API easier to use, then that sort of tips the scale towards the use of RDMA. On the other hand, if we accept that our NICs should be fancy RDMA NICs, well, then exactly how fancy should they be? Like, how much functionality should we put into them? And further, since we have this special hardware that we're going to put into our data center anyway, how should we manage this special hardware's interactions with the other kinds of special hardware that people are already deploying? I'm not going to get into this other hardware trends side of the story, but other preview sessions will. So to explain what's happening at all of the other ATC and OSDI sessions. So moving on, if this first session we talked about was all about this one specific technology, RDMA, the other networking session that I've been asked to preview is really more about showcasing just how much breadth networking has as a field, or a problem domain, depending on who you ask. We have papers about data centers and designing networks with latencies in the microseconds, with all the way to dealing with satellite or Wi-Fi wireless networks with latency in the hundreds of milliseconds. And that's 5 or 6 orders of magnitude of latency in just one session. And again, I'm not going to attempt to cover all the topics that the papers cover, but rather just provide a general overview of a couple areas that I think are interesting. So the first area is of course data centers. So traditionally, data center networks were composed of switches that look like a fat tree. This type of network was revolutionary a decade ago because each of the switches was identical and could be bought sort of commercially off the shelf, and therefore it was much less expensive to build than those previous like HPC clusters. However, what the users of the data center wanted, which I've sort of demonstrated here by grabbing a picture of the data center network from a paper in SIGCOMM 2018, is the abstraction of one big switch. So the dream is that servers can communicate across the network, and the only bottlenecks happen when there's incast, or like multiple servers try to talk to the same server. Obviously, then there's going to be problems, but other than that, the abstraction that people want is that if 2 unrelated hosts are talking to each other, they shouldn't interact at all. The data center network architecture on the left doesn't really get us all the way to this abstraction, however. There's an entire line of work on what's now called load balancing, or how we should route packets among the multiple available paths so that we get as close to the one big switch abstraction as possible. For example, one extreme we can use is to randomly hash every single packet to pick the path it'll take. And this will use the core part of the network pretty efficiently, but it'll cause more reordering because packets from a single flow might be taking multiple different paths. And this makes things more annoying for applications. On the other extreme, you could keep each flow to a single path, which is pretty simple for applications. But if 2 long flows get hashed onto the same path, then we end up with congestion and therefore lower utilization of our expensive network. The questions with these schemes that you generally want to keep in mind are, how complicated are they to implement, and what kind of application performance can they support? Another interesting question that we can consider that spans the various layers of magnitude that we've been talking about is congestion control, which is answering a pretty simple question with a pretty complicated answer. And the question is, if we're sending data over the internet, how fast should we send? If we send too fast, we might starve others, which is the tragedy of the commons problem. And if we send too slow, we might give up opportunities to send sort of without any point. We might have been able, it might have been fine if we sent faster, and we could have gotten more done. This is a really well-studied question, and there are basically 2 axes of philosophies that people end up siding on. The first is the sort of universality axis, or how general a single congestion control algorithm should expect to be. And for the first 2 decades of congestion control, the balance was pretty firmly on the side of universal congestion control algorithms because there were basically only 1 or 2 Reno, and Cubic, and they were deployed really widely. But after a while, people started proposing domain-specific congestion controllers, for example, DCTCP in data centers and Sprout in cellular networks, and people have been building on the sort of domain-specific congestion control ever since. On the other hand, there are also people who argue that a single congestion controller should be able to adapt to a variety of different situations, and sort of having a domain-specific congestion controller is overkill. Around the same time, in our other axis, machine learning was becoming popular, and people started working on applying it to congestion control. So in theory, the benefit this has is that a non-learning approach will encode in it some model of the network. So for example, one model could be that there's a single bottleneck queue between the sender and receiver. This might be a reasonable model. It worked pretty well for many congestion controllers, but it might not be a reasonable model either in some parts of the network. And the argument is, wouldn't it be great if there was no underlying model at all and our algorithm just adapted to whatever conditions it happened to encounter? The counterpoint that people make is even a machine learning approach will encode in it some model of the network, either in its utility function or the way it was trained or somewhere else, and that by hiding away this implicit model, we lose our ability to reason about it and our ability to improve the algorithm. We can also think about how this relates to the universality argument. If there's truly no model, then a good learning algorithm should be universal. If you want more background on this debate, then the Congestion Control Throwdown paper from Hotnets 2017 is a good place to start. And the questions to keep in mind here are, what are the hidden modeling assumptions of any machine learning approach, and how general can it be? So thanks for listening to this topic preview session, and remember to go to the 2 networking sessions for the latest research in networking. If you have any questions on about the topic I covered, or you want clarification on networking topics at OSDI or ATC this year, then you can email me and I'll be more than happy to talk more. Thanks.